We're continuing our discussion about the different reactions that are possible to synthesize alkyl halides. And we're going to focus on radical-based substitution reactions. Again, this reaction, alkane plus a halogen, is very familiar to us. We know our initiation, propagation, termination reactions that can lead to alkyl halide products from this reaction. But we haven't really looked at those substitution reactions when we're using an alkene instead of an alkane. And there's some important differences and a new concept that we need to understand in order to think about these reactions. So let's look at one of these reactions now. We're going to start by brominating an alkene. And so we'll have our bromine here. Now we can either have bromine in the presence of UV light form, right, that UV light splits our bromine-bromine bond in an initiation reaction to give us our two bromide radicals. Often you see a different reagent than just bromine, a sort of more convenient reagent that we use. And you don't need to know the structure of it, but I'll draw it out here. This is N-bromo-succinimide. And you don't see the structure that often, but it's abbreviated NBS. And you will see NBS a lot. You can think of NBS as just an alternative source of bromide radicals. You still need the high energy light in order to break this bromine off of the NBS, but either of these two reagents, bromine or NBS in the presence of UV light, can generate these bromide radicals in an initiation reaction. So far you're just the same as the alkane, but let's react this with an alkene and we'll see what the difference is here. So let's look at a terminal alkene, one with a double bond at the end. And what we found is that there's some specificity for which of the hydrogens in this alkene, the bromine or the bromide radical, substitute for. And it turns out they substitute at allylic positions, right? Allylic positions are ones that are not part of the double bond, but are on the next neighboring carbon to the double bond. So if we look at this alkene, we can say that these two carbons are part of the double bond. They're actually called vinylic. This is the neighboring carbon, and this is our allylic position. We mentioned this word before. It's supposed to be an A-L-L-Y-L-I-C. So let's do this reaction with the allylic position and then see why it happens there. Sort of, we're going to do a reverse argument. Let's just try it here and see what happens. So there are two hydrogens available for substitution at this allylic position. If we draw the mechanism here, show that the bromide radical can steal one of those electrons. The other one will just stay on the carbon chain. This will generate one of our final products of these radical substitution reactions, HBr. But in a propagation reaction, we've just switched where that radical is. It's now on the allylic position of this alkene. So the reason why this happens often is because this allylic radical is more stable than other radicals. The reason why it's more stable is because it's stabilized through resonance. That means we should be able to draw a resonance structure for this intermediate, and we can. One of the electrons from this double bond can come in between these two carbons to join the radical electron. That shifts where the double bond is. This is a double arrow showing we've got a resonance structure over here. Now the double bond is in between these two carbons. There we go. And this electron is left out by itself as a radical. Okay, so we have moved the pane of this radical through the molecule through resonance, and that leads to two different products. Right? We used one of our bromide radicals here in this propagation reaction to generate the carbon radical, allylic radicals. And then our second bromide radical can come in and terminate this reaction on either of these structures to generate two separate substitution products. In this first avenue, our radicals on this carbon, so our bromine can terminate there. In this reaction, our radicals at the end, our double bond has switched positions. And so we get two separate substitution products. Now, what you'll notice throughout this mechanism is that our radical intermediates are always still allylic, right? This extra electron is not on the double bond, but it's on the neighboring carbon here also. And our final substitution products, the bromine has substituted at the allylic position. If ever you go through a mechanism and you get something that's not allylic, you should check your work because it's probably incorrect. Okay. So these are two predicted major products from the radical bromination substitution reaction on this particular alkene. Which of these do you think might be more prominent, a better major product? Well, we know a little bit about radicals already, and so if we were to choose which of these radical intermediates is more stable, we would say, well, both are allylic, which means they're resonance stabilized. This one's on a secondary looking carbon, and this one's on a primary looking carbon. So if I were forced to choose, I would say this one's probably a better major product than this one. Even though both are allylic, this is allylic and secondary, so that radical can be stabilized not only through the resonance effects, but through maybe inductive effects from its rich neighbors. The inductive stabilization of this radical would be less because it just has one nice neighbor.